Hello, my students. I'm recording this video, right, to go over the lab number 6, right, talking about the equilibrium constant. Right, the reason I'm doing this again because I have received concern about the coronavirus from several students. Right, so that's why I made this lab optional, meaning that you have the option to perform the lab or watching this video. Right, so I highly encourage you to perform the lab because I think lab is more interesting than the lecture. Right, so if you still want to perform the lab, all I need you to do is just send me an email, and after I get a number of the students, I can prepare the materials accordingly. Right, so hopefully if you want to do the lab next week, hopefully you can send me the email before Monday. Right, so I will prepare the materials during the lunchtime. Right, so about this coronavirus, I want to talk about it before I get into the lab. Right, so right now in the United States, we have almost 750 confirmed cases. Right, so this number is increasing like crazy every day. And for the state of Georgia, we are the number 5, right, the 5th highest confirmed cases, right, without considering the 2 cruises, right, which is gonna be parked near the United States. Without considering those 2 cruises, we ranked number 5 in terms of the number of confirmed cases. Right? I think we have 18 right now. Right, so as many of you might heard today, we have confirmed a case, right, who is a high school teacher or middle school teacher in the Fulton County. Right, so the Fulton County, all the public schools gonna be closed tomorrow. Also learned that a daycare teacher at Oglethorpe, Georgia, also confirmed. So I just highly suggest everybody to be careful, right? So take many precautions and wash your hands more frequently. Try not to touch your nose, touch your face, or touch your eyes, right? So we have these sanitizers all over the campus in the building, right? So every time you use a restroom or enter a classroom, when you touch those door handles, try to clean your hands. Right. So let's get back to the lab. We're gonna measure the equilibrium. Some of you might not learn chemical equilibrium yet in the lecture, right? So that's what chapter 17 is all about. Right, so in chapter 16, we taught the chemical kinetics, which is related to the rate of a chemical reaction, right? So how fast the reaction proceeds. In chapter 17, we're talking about chemical equilibrium, which is the extent of a chemical reaction, right? So the extent meaning that like how much reactant can be turned into products, right? So the more products formed, the higher the extension of the reaction. Right, so in this lab, we're going to calculate the equilibrium constant for this chemical reaction. Right, so for the reactants, we have iron 3. Right, so iron 3 plus is also called ferric. Right, so for iron 2 plus, it's called ferrous. And the other reactant is called thiocyanate. Right, so it's SCN with a -1 charge. Right, so when these two ions are mixed together, they will form a complex. Right, so has a formula of FeSCN2+. Right, so the 2 plus is calculated based on the overall charge of these two reactants. Right, so from the +3 of iron, right, minus the -1 charge from the thiocyanate. Right, so actually this FeSCN2+, right, this complex is the main component of fake blood. Right, so in the movies or in a lot of pranks, right, we see this fake blood a lot because that's just a burst of this bag of this fake blood solution. Right, so you see someone get shot, right, that's actually the explosion of the fake blood bed, right, hidden in their body. So to calculate the equilibrium constant, we're gonna use this equation. So on top we have the concentration of the product, right? So below we have the concentration in terms of the reactants, right? So in this case, because the coefficient of everything in this equation is 1, right? So we don't have to worry about the exponent for these concentration terms, right? But if, for example, there's a 2 in front of the iron 3, right? So in that case, we will put a square, right, exponent 2 on the concentration for iron 3, right? So take the coefficient into consideration, right? So the ratio of these concentrations is equal to the equilibrium constant, right? So this Kc, so meaning that this concentration must be at equilibrium, right? Meaning that the concentration no longer changing, right? So the Kc here, the K means the equilibrium constant, C means it is concentration based, right? Sometimes you see something like Kp, right? That means it's the equilibrium constant based on the pressure, but that's when we talk about the reaction involve gas only, right? So, but that's not very commonly used, right? Most time people use Kc, right, to represent this equilibrium constant is concentration based, right? So again, I want to emphasize this, right? This Kc must be calculated using the equilibrium concentration, right, which is doesn't change anymore, right? So it's a constant concentration. So this product, this fake blood, right, has a red color when it's concentrated, right? So in this lab, we cannot generate that high concentration of fake blood, otherwise it's gonna be out of the detection range, right? So the concentration of this fake blood we're gonna produce is fairly low, right? So instead of having a red color, the low concentration of fake blood actually has a orange color, right? So as we learned from the second lab, the Beer's law lab, right? So we can use this complementary colors chart to determine what type of light, right, this orange solution is going to absorb, right? Because it has an orange color, it's going to absorb the the color of the opposite end, which is blue, right? So the blue light has a wavelength around 450, right? So that means a orange solution will absorb most amount of the blue light, right, compared to the other colors. So in this lab, we're gonna use a wavelength of 447. Right, so at that wavelength, this low concentration of fake blood is gonna absorb the most amount of light. Right, so that will give you the highest sensitivity. So it means the highest absorbance. Right, so from the previous slides, we know how to measure the concentration, right, of this fake blood, right, by using its absorbance and the Beer's law. Right, so for part 1 of this lab, we are gonna build a calibration curve, right, to for the standard of fake blood, right. So using this calibration curve, we can calculate the concentration of the fake blood generated in part 2, right. So in part 1, we're gonna prepare 5 standards to build this calibration curve. Again, the standards meaning that is the sample with a known concentration, right? So in this case, it's the sample with a known concentration of fake blood, this FeSCN2+, right? So in your handout, table 1 shows you the recipe for making these 5 standards, right? So because we don't have this FeSCN2+, right? We don't have this fake blood standards, right? So we're gonna mix the reactant, right, to generate a known concentration of this fake blood, right? So you may wonder, right, how can we generate this known concentration of fake blood, right? Because this is a reversible reaction, right? So from this recipe, you can see that the the concentration of the iron 3, right? So the iron 3 comes from adding the ferric nitrate. Right, so in this ionic compound, iron is a +3 charge. So when they dissolve in water, it totally dissolute. Right, so the iron 3 will be totally separated from the nitric ions. Right, so the nitric ion will be the spectator ion. Right, so it's not gonna be involved in the reaction. Right, so see this concentration of this iron 3 solution we add is 0.02 right, molar. Right, so this compound it dissolve in also have acid, right? Also have nitric acid. Right, so we want to decrease the pH of this solution, so the iron 3 doesn't precipitate. Right, so if we don't control the pH, the iron 3 will precipitate. Right, so that's gonna affect the data in our lab. So if you look at the concentration we add under the volume, right? So we add 5 meter of this 0.02 molar iron 3 in all your standards, right? For the thiocyanate, right? So the thiocyanate comes from a potassium thiocyanate. Again, this is an ionic compound, right? So it will totally dissolute. So the potassium will be the spectator ion, right? So it's not gonna involve in the reaction. So for this thiocyanate ion, right, the concentration we add is 10% of the concentration of the iron 3, and also the volume is also lower than the volume of iron 3. So when you calculate the final concentration or the initial concentration of the reactant, right, so after taking the dilution factor into account, you can see the concentration of thiocyanate is much lower than the concentration of iron 3. Right? So in this case, because iron 3 concentration is way higher than the thiocyanate, we can assume that all the thiocyanate has been reacted. All right. So this is a picture I took right during the lab. So after I turn on the instrument, I adjust the wavelength to 447, and remember the first step, right, is calibrate your instrument or using a blank, which is a DI water, right, to calibrate your instrument. So I put the DI water in, and I adjust the knob, right, to make the absorbance equal to 0. So then later follow this recipe, right? So I prepared this 5 standards. So in the picture on the left, you can see this 3 flasks, right, containing this 2 solutions and the DI water, right? So on the left, that is the iron 3 nitrate in the nitric acid, and the one in the middle is the potassium thiocyanate. The one on the right is the DI water. And you see they all are colorless, right? So they are no color at all by themselves. And I have 3 pipettes, right? So 1 for each solution. So follow this recipe in table 1, right? So I mix the corresponding volume, and I mix them in the test tube. Right, so again, as mentioned in the previous slides, right, so because the concentration of the iron 3 we added is way higher than the concentration of the thiocyanate, right, so we assume that all the thiocyanate you added has been converted to this FeSCN2+, or the fake blood, right, so the fake blood concentration is actually equal to the initial concentration of this thiocyanate. Right, so after I mix them, follow the recipe in 1, I have this 5 standards, right? So you can see from left to right is number 1 and then to number 5. Because you can see the color, right? The color gets darker, right? Because more fake blood has been generated. Right, so because this test tube is too large, right, so then I transfer some of this mixture into the cuvette, right, the smaller test tube, which we can put into the sample holder of our spectrometer. Right, so again, you can see the volume in this cuvette is different, but that's totally fine, right? So we want to add enough volume in the cuvette, right, to make sure the light is can go through, right? So this is way enough than the required amount, right? So no matter how much we add, right, the concentration doesn't change, right? So we should have the same absorbance, right? So here the table gave you the absorbance of these 5 standards I measured, right? So in this table, on the left hand side, right, it is the same as table 1, right? So on the last column, it gave you the absorbance, right? So you're gonna put this number in the Excel template I uploaded on Moodle, and for the fake blood concentration that produced, right? So again, in the previous slide, we mentioned that the concentration is going to be equal to the initial concentration of the thiocyanate you added, right? So this calculation, instead of giving to you, I want you to calculate it, right? So based on this volume and the concentration in table 1. So using this M1V1 equal to M2V2, right? Using this equation. So it's very similar to what we done in lab, the iodine clock lab, right? So we mix those reactants, right? So then calculate the concentration after we mixed everything, right? So this is for you to be calculated in the Excel template, right? So once you get the concentration of this fake blood, FeSCN2 plus, and the absorbance which is given, you can actually build the calibration curve. Right, so the calibration curve, right, again we put the absorbance on the y-axis and the concentration on the x-axis, right? So every time you want to plot this, something like this, think about which one is the dependent, or which one is the changing factor, right? In this case, absorbance depends on the concentration, right? Where concentration is our changing factor, right? We change the concentration, and different concentration give you different absorbance, right? So we need to put the concentration on the x-axis and the absorbance on the y-axis, right? So when I grade your previous report, right, some of you always, right, switch the axis, right, give you the wrong result, right? So this calibration curve is just an example, right? So after you plot this absorbance data, right, it should give you this linear chain line. So in Excel, you can find the equation of this chain line, and using this equation, right, to find the relationship between the absorbance and the concentration. So that's all for part 1. In part 2 of this lab, we're going to determine the equilibrium constant Kc for this chemical reaction. As we talked about earlier, right, in order to calculate the equilibrium constant, we must use the equilibrium concentration of everything in this chemical reaction. Right, so this concentration must be the equilibrium concentration. Right, so table 2 in your handouts, right, give you the recipe, right, for making these 3 samples we're gonna use to measure the equilibrium constant. Right, so we're gonna add 5 milliliter of iron 3 solution, different concentration of a different volume of thiocyanate and a different volume of DI water. Again, the total volume is 10 milliliter. You have the same amount of iron 3 but different amount of thiocyanate. Right, notice that with the concentration of the thiocyanate is still 2 times 10 to the negative 3 molar as we have in part 1, but the concentration of iron 3, right, decreased, right, from part 1. In part 1 we have 10 times the concentration of this one, right? So in part 1 we have 0.02 molar. In part 2 we have 0.002 molar, right? So it's actually the concentration is same as the thiocyanate, right? So because they have same concentration, right? So after you mix them, because you add more iron 3 than the thiocyanate. So the after you calculate the concentration after mixing, or using M1V1 equal to M2V2, you can see the concentration of the iron 3 will be higher than the concentration of the thiocyanate, right? But it's only like one-fold or two-fold higher. It's not like that high, that much higher as we have in part 1, right? So in this case, we can no longer assume that the thiocyanate is 100% converted to the product, right? So only part of the reactant has been converted to the product, right? So at the when the equilibrium reached, right, some of the reactant still remain unreacted. Alright, so in this part, we're gonna try to figure out this equilibrium concentration for not only the product but also the reactant. Alright, so for this sample, so recommended by this recipe in table 2, I made these 3 samples, right? So showing in the picture on the right. So you can see this 3 test tubes containing this solution 1, 2, 3. Right? You can see the color gets darker as we add more thiocyanate. Right. So then I pour these solutions into the cuvette and measure their absorbance. Right. So the table down below, right, gave you the absorbance of the 3 samples, right? So this is again the volume we add for each test tube, right? So the same as we have in table 2. So the absorbance is given, so that's what I measured. And for the concentration of the fake blood, right, the FeSCN2+, that is for you to calculate using the calibration curve you built in part 1. Right, so after you get the equation of this trend line of the calibration curve, you can convert the absorbance of the 3 sample into the concentration of this fake blood. So once you figure out the concentration of this fake blood, the product, right, using the absorbance, we can actually create something called the reaction table, right? So to calculate the equilibrium concentrations, right? So if you're in my lecture, we already done a few examples about how to use this equilibrium, the reaction table, right, to calculate the equilibrium concentrations. But if you haven't done so in the lecture, you're probably gonna do it very soon, right? So I'm gonna just spend a few minutes to explain what is a reaction table, right? So for a reaction table, first you're gonna write down this chemical reaction, right? So then you create a column, right? So saying initial concentration, change in concentration, and the equilibrium concentration, right? So based on what is given, right, you can fill in the known values in this table and use it as a tool to calculate the unknowns, right? So for example, in this part of the lab, because we mix the known concentration and the known amount of the reactant, right? So based on the recipe in table 2, we can use M1V1 equal to M2V2 to calculate the initial concentration of the iron 3 and the thiocyanate after we mix them, right? So that will be the initial concentration for the reactant. And because we didn't add any of these products, right, so this concentration will be 0. So for the change of concentration, right, so after the reaction is completed, right, so when the equilibrium is reached, the absorbance of the sample, right, we can convert that into the concentration of this FeSCN2+, right? So for this unknown value, right, so we can convert the absorbance into this X. Sorry, so this X indicates that this is a change of concentration, right? So it's an unknown value, right? So based on our absorbance data, we can actually, right, calculate it. All right, so for this X, right, because the product is produced, right? So we put a positive sign to indicate, right, we're actually generating it, right? So at the same time, right, we are consuming the reactant, right? So we put negative sign, right? So we have the change of concentration of the reactant will be a negative x, right? Notice that this coefficient in this equation is 1, 1, and 1, right, for all the reactant products. So we have no multiplier in front of this unknown concentration x, right? So in case we have a coefficient, right, in this reactant product, we should also put this coefficient, right, in front of the x, right? For example, if you have a 2 iron 3, with the change of concentration of iron 3 will be minus 2x. So for the equilibrium concentration for iron 3, it's going to be equal to the initial concentration minus x, and for the thiocyanate, similarly, it's going to be equal to the initial concentration minus the x, right? And for the product, it's going to be 0 plus x, which is positive x, right? Again, x is obtained from the absorbance, right, of your sample using the calibration curve you developed in part 1. So once you get the number of these equilibrium concentrations, right, you can substitute these numbers into this equation to calculate the equilibrium constant. So check your Moodle website. So I upload this Excel template for you guys to work with, right? So the table on top is for part 1. So we had the volume of each reactant and the DI water added in each test tube. You can find the absorbance in the slides, in the previous slides. And for the concentration of the product, you can calculate, right? So again, in part 1, this concentration is actually equal to the initial concentration of the thiocyanate, right? So plot absorbance versus the concentration, right, to generate the calibration curve. So I suggest you put that calibration curve in this top right blank region. Alright, so the table below is for you to calculate the concentration in part 2. Right, so again, I give you the volume, right, same as the table 2. Right, so you're gonna calculate the initial volume of the reactant using M1V1 equal to M2V2, and you can also find the absorbance in the previous slides, and then using the Beer's law, right, convert the absorbance of the sample into the concentration of the fed blood, and then using the reaction table, figure out the equilibrium concentration of the reactants, and then calculate the equilibrium constant. Right, so everything must be calculated using the mass function in the Excel, right? You cannot calculate using the calculator and then put a number in there, right? So remember to upload the Excel on Moodle, and I will check whether you have put the correct calculation, the equation, into each cell. For the lab report due next week, I will set the deadline to Wednesday. Alright, so on Moodle, you need to upload your Excel, and also some of you asked me about the pre-lab, those things you wrote in the notebook, and please take a photo of it and upload it together with your Excel. Right, so the package also due before Wednesday, so please drop it off outside my office. The package should include the cover page, the post-lab questions. I think there are only 2 problems, right, and the sample calculation. Right, so you don't need to show me the calculation for every sample, right? So just 1 sample for each part, and also the Excel you printed. And for the cover page, also include your session number, right? So Monday afternoon is session 001, Tuesday morning 002, and Tuesday afternoon 003. Right, so also after you finish watching the video, let me know what you guys think. Right, so again, I encourage you to come to the lab, but that is optional. Right, so if you decide to perform the lab instead of watching this, you need to send me an email. Right, so I will prepare the materials accordingly. Right, thank you.